Okay, let's start. So today we'll start our discussion on memory hierarchy, on the topic of how memory is arranged in microprocessors. Okay, intentionally we are skipping over the pipelining part. We will come back to pipelining part, the detailed microarchitecture of processor design as the next topic. So for now, we'll continue on discussion on memory. The most important thing to understand here is that memory is arranged in a hierarchical fashion in modern computers. In modern computers, it is not that you have a monolithic memory where everything resides at the same time and you execute things from there. It does not work like that. It works in a different, more complicated fashion, and that's what we are going to learn here. Later on, when you study operating systems in the next semester, you will also be introduced to greater details of what role the operating system plays in making this possible, this hierarchical memory structure possible. Okay, so there are many reasons for having a hierarchical memory structure. As we will go on studying this topic, we will understand some of them. The basic reason why it is possible to work with relatively less amount of memory is something called principle of locality. Okay. What is principle of locality? In very simple terms, it means programs access a small proportion of their address at any given time. Okay. This small proportion of their address is a very important concept. A 32-bit program, a 32-bit address space program theoretically have an address space spanning from address 0 to address 2 power 32. Some of it is reserved, but remaining can be used. However, most programs do not use that much of memory, and that's what makes it possible. Okay. Most of them are limited to a small subset of all possible addresses. Two types of localities exist. One is called a temporal locality and the other is called a spatial locality. Okay. What is temporal locality? That the items which have been accessed recently are likely to be accessed again soon. Okay. This is the way human beings write program. Such constructs are very, very common. For example, instructions in a loop, induction variables, etc., etc. And what is spatial locality? Spatial locality is that items which are near those which have been accessed recently are likely to be accessed soon. Okay. So if I have accessed an instruction I, the instructions which are near to I also are likely to be accessed soon. Okay. Either exactly the next instruction at I plus 1 address or I plus 4 address in MIPS, I plus 4 address will be accessed because that is sequential execution. Or what might happen? There might be jumps, but what is the length of these jumps? The length of these jumps are also, jumps or branches are also not that long actually in real programs. So if you have brought in certain portion of the program or some amount of data which the program is working on into memory, the chances are that many of the items that you have brought into memory will be accessed. For example, in an array, if you access the first element of the array, I am talking in terms of data. Suppose you are performing an array processing. In our class, in your tests, in your labs, you have performed such assignments and you have seen examples where array processing is being done. If you have accessed first element of the array, the chances are that you are also going to access the next, second, the third, the fourth elements of the array very, very soon. So you can bring in certain chunk, a certain amount of data from the array. If the array is too large that the entire array will be difficult to bring into memory, still, if you bring in certain portion of the array, the chances are that your needs will be satisfied for certain amount of time. The basic problem is that taking that our memory becomes more and more expensive if it has to become faster. Okay, expensive in terms of amount of money you pay per unit storage. Okay, just a moment. Give me just. Okay, so sorry about the interruption. So because we cannot afford that much of fast memory because of implement something called a memory hierarchy, and I take advantage of this principle of locality. Okay, if this principle of locality had not been observed in computer programs, it would have been difficult to actually adopt this memory hierarchy. What is a memory hierarchy? At the bottom of the hierarchy, well, let me just, maybe I can just draw. At the bottom of the hierarchy is your hard disk. Is your hard disk drive or HDD. Above that is your DRAM. This DRAM is usually called the memory. So when I call memory, by default, I mean this DRAM. Okay. On top of that DRAM is your something called a cache memory. This is inside the CPU, and beyond the cache memory is your registers. Now, and this cache memory and register, these things typically are inside the CPU. Okay. This is the typical memory hierarchy in a modern computer. We have already studied about registers. Notice that I have drawn the sizes in the relative order. The hard disk drive is the farthest away from the microprocessor and it is the largest. It is also the slowest, followed by the DRAM. The hard disk drive typically in a modern personal computer typically is in the order of 1 terabyte or so. The DRAM is typically in the order of 8 to 16 gigabyte. The cache memory is in the order of 6 to 12 megabytes. The cache memory itself has several levels. We will study it, but the total size of cache memory in an ordinary computer, ordinary personal computer would probably be 12 megabyte or so, or less than 15 megabytes probably. And you have certain number of registers. The number of registers is fixed by the microprocessor architecture you are using. So how it works is we store initially everything on the disk. However, rule 101 of, I think I discussed it earlier when we discussed MIPS assembly language programming. Rule 101 of accessing memory is that the microprocessor cannot directly access the hard disk drive. The hard disk drive to a computer is actually an I/O device, okay, which is kind of surprising that a device which holds major amounts of program and data actually is an I/O device and is not theoretically a mandatory part of a computer, but that's how a computer works. The microprocessor interacts primarily with the memory chip, that is your DRAM chip. Excuse me. Okay, so because the DRAM chip is much smaller than the hard disk drive, you access certain amounts of program and data from the hard disk drive, put it in the DRAM chip, but access to the DRAM chip from the microprocessor is quite slow. It is affected by something called von Neumann's bottleneck, where 10 to 100 clock cycles might be wasted for the access of this data. So from memory. So the microprocessor tries to bring in even smaller amount of data whose probability to be getting accessed is even higher to its on-chip cache. On-chip cache memory is very fast in a sense because it is inside the chip. Access to cache memory, searching the cache memory of whether it is there, and if it is there, returning the value from the cache memory to the microprocessor registers, everything can happen inside one clock cycle, one CPU clock cycle. Okay. And finally, the microprocessor works exclusively directly on the registers. They cannot work directly with cache memory or things. So finally, when the things are in the registers, from cache to registers they are brought, the microprocessor operates on them, and then when you store the value back, you store the value back to cache, then to DRAM, and then if needed, you update it in the hard disk drive. We will study. There are several complications related to this storing back the value and reading in the values. Many issues are involved. As time goes on, we will discuss some of them. Okay. So whatever is the recently accessed value or whatever is needed, that is brought from the disk to the small DRAM memory, and then from the DRAM memory it is accessed to the SRAM memory. This SRAM memory is basically your cache memory. Okay. DRAM is dynamic RAM, dynamic random access memory, and SRAM is static RAM, static random access memory. Random access memory implies a memory where the access time does not depend on the address. Okay, where the amount of time needed to access a value, to read the value, or the write to a particular location does not depend on the address. The hard disk drive is not categorized as a random access memory because, as we will find very soon, Unfortunately, the hard disk drives have certain peculiarities, which means that the time it takes to read or write a value to a particular location on the hard disk is variable. Okay, it is very peculiar, but that is what we'll see. So the transfer of data between the microprocessor, registers, cache memory, memory, etc., always happens in blocks. A name, common name for the block is also a line. This is a very peculiar name, but that's the name that has become standard. Okay, line. When you hear of this, you think that it has got something to do with electrical wires or things like that. But here in this context, it means an block or amount of data. Okay, it is the unit of copying. The unit of copying might be one word, or typically this nowadays it is multiple words. Say for example, a reasonable example is half kilobyte or 1 kilobyte. Okay, half kilobyte is 512 bytes. One word is 4 bytes. So you can divide 512 by 4. So 128 words. 4 byte words is one block. If it is a 1 kilobyte block, then it is 256 4 byte words, etc., etc. Makes one block. What is the size of the block is a parameter in the design of your microprocessor. Typically, the size of this block in modern microprocessors can be made variable in a sense that how much in chunks of what size you are going to read in the data, at least from the hard disk drive to the memory, at least this portion, that can be made variable. It can range up to megabyte size, 16 megabyte, 32 megabyte, that means very large chunks are also possible, ranging from 1 kilobyte or even a half kilobyte. So it's a large range. Now, because the cache is inside the chip, ideally I would have liked everything to be inside the cache memory. The cache memory is a small SRAM built memory. SRAM is a very fast technology. Every SRAM bit can be implemented with about 6 transistors. Every DRAM bit can be implemented using one transistor. There are some additional control circuitry which gets amortized over the entire chip. So the overhead is something like, say, per bit of memory DRAM is say 1.05 transistors, something like this, and for every SRAM it is something like 6.1 transistors per bit, something like that. The SRAM cells used in a cache memory are slightly more complicated. In cache memory, every bit is about every bit, the two common designs, there is a 9 transistor per bit design and there is a 10 transistor per bit design. Both of them have their relative advantages and disadvantages. These two are popular. Plus, there is some control circuitry. Okay, so it is slightly more complicated than the technology is similar to SRAM, but it is not exactly SRAM. It is more complicated than SRAM. Okay. Now, I would like really like that everything, all data will be found in the cache memory, and there would be no need at all to go to the main memory. Okay. Unfortunately, as we will also see in this chapter, that cannot happen in any real computer because of several types of constraints on the size of the cache memory, the way the computer works, etc., etc. It is not possible to have everything that you need for a program, all the code and all the data to be inside the cache memory. That is not possible. Okay. But it is good if we have it. So if the if the upper level means upper level here, this processor is the upper level basically. Okay, so if the processor is searching for data and if it is found, it is called a hit. So I want my hit ratio ideally to be almost 1. Okay, so that most of the times the data is found. What if the data is not found? It is called a miss. So I want my hit ratio to be almost 1 and I want my miss ratio to be almost 0. Because if there is a miss, I have to go and search into the lower level of memory, which is DRAM, which is slow. If it is not found there, I have to go further down and search into the main memory, into the hard disk drive. That is a severe problem actually. If you have to search something from the hard disk drive, it can take millions of clock cycles, means crores of clock cycles basically. Okay. That's why when you are invoking a program for the first time, the executable, not the entire executable, it doesn't work like that the entire executable is loaded into memory, but at least some parts of the executable are loaded from hard disk drive to the main memory, and from that part of it is loaded on the cache. Then some parts of it are copied to the registers and it starts executing. Initial latency of when the software is getting invoked is very, very large, because the software, the necessary instructions and data, nothing was there, okay, in the main memory. So this is called a mandatory miss initially. There is no way you can avoid this miss when something is invoking. And if the software that is invoking is a very large software, okay, like say MS Word, anything of MS Office, the web browsers, this MS Teams, etc. It takes a lot of time. Of course, it helps if your lower levels of memory are faster, but magnetic disk, they have certain speed limits, as we will find. So people have come up with other technology to make it faster. We will study. I mean, we'll just mention them. So this static RAM, dynamic RAM, magnetic disk, you will find that the access times. So the access time increases, or I should write speed decreases as you go down, and cost increases as you go up. Okay, these prices that have been given are very old fashioned. Okay, I don't believe them. I think the cost nowadays has become much smaller. These are quite old estimates, but the trend is similar. Okay, the trend is still similar. So an ideal memory, the search for which continues, should have the access time of SRAM technology. That means it will be very fast. And the cost will be, capacity and cost will be similar to hard disk. That means it will be large and cheap. So this combination is ideal, but whether it can be achieved or not, that future technology will tell. So let us just go through some DRAM, basics of DRAM and hard disk drive. And cache memory we will study in detail, maybe not in today's class, later on. So in DRAM, data is stored as charge on capacitors, very, very small, not added capacitors. The capacitors which are inherent in MOSFETs, these are extremely small capacitance values, and these are leaky transistors. Leaky transistors, in a sense, if you store a charge on these capacitors, the charge actually it leaks through the transistor. Okay, so they have to be refreshed periodically. These capacitors have to be refreshed, or this DRAM have to be refreshed, otherwise it forgets. Okay, so this read and write, these things can be performed automatically by the control circuitry that is present there. You as an user do not need to bother about these things. Now, bits in DRAM are typically organized as rectangular array, and the DRAM accesses an entire row. However, see, usually you would not access only one word. If you are accessing data from memory, we mentioned principle of spatial locality and temporal locality. If you are accessing one word from memory, chances are you are going to access further information, further instructions and data from somewhere close by very, very soon. So it supports something called a burst mode, where successive words from a row can be accessed, okay, together. So your initial access latency is distributed over the entire large amount of data that you are fetching in. We'll see what we mean by that with an example. Then there are these advanced DRAMs, double data rate DRAM. Double data rate DRAMs, usually the DRAMs are clocked circuitry. Usually, you know, clock circuitry, they operate at a particular clock edge, either the positive edge or the negative edge. The DDR DRAMs, they can transfer data on both the positive clock edge as well as the negative clock edge. So in a clock cycle, basically they perform operation twice. Okay, and so they increase the throughput by a factor of 2. Then there is quad data rate. In ordinary DRAMs, it is not possible to perform read and write at the same time, because read and write happens through the same port. Port is the interface of the DRAM circuit with the rest of the system. Okay, read and write cannot be performed together because they happen through the same port. However, in QDR DRAMs, there are several dedicated ports for input and outputs. So in that case, you can perform inputs and output operations, of course, on different address ranges through two separate ports, and each of these ports are working at both the positive clock edge as well as the negative clock edge. So overall, you have a 2 into 2, twice 4 amount, I mean, a factor of 4 throughput, basically. This is a plot to show how the prices have fallen. This is like how the capacities have increased and how the prices have fallen. This is a 2007 estimate. Okay, this is very, very old. So we are like 14 years ahead, and DRAM technology is even like it is more advanced even than microprocessor technology. Okay. Now, there is also this synchronous DRAMs, and there is this row buffer, which allows several words to be read and refreshed in parallel. There is synchronous DRAM, SDRAM, which allows for consecutive accesses in burst without needing to send each address. You can send an address range and that entire thing is read. You need a buffer to hold this thing. Now, there is also a concept of DRAM bank. Many computers have multiple DRAM chips. Okay. How they can be arranged with only one memory bus is called a DRAM banking. We will come to it, and it improves bandwidth. Now, these are possible organizations of DRAMs. Okay. There is a concept called a bus. A bus is it is a shared connector. Here in this example, it makes it look as if the memory is getting accessed by only the cache memory. Later on, we will study that that is not the case. The memory is a resource which might be accessed by many other devices also using the same memory bus, where the processor itself is kind of a shared connectivity for this memory to connect. The bus provides the shared connectivity to the processor and other devices to memory. You might have said, why do other devices need memory? Well, we'll study very soon that other devices also have a lot of use of this DRAM. Okay. So one of the simplest organization is that my bus width is 1 word. At every point you read only 1 word or write only 1 word at a time. However, that might not be very efficient. Okay, because every clock cycle you are reading in 1 word. Just now we discussed this principle of locality, that probably reading multiple words will be useful. How do you do that? You make the bus wider like this. So this is a wide bus. Okay. So now maybe you can read in 3 or 4 words at a time from memory. Of course, your memory has to support that. That electronics interface has to support that. And your cache also can read in more than 1 byte. So that is what I mentioned, like the block concept. It reads in a block at a time. Okay. Now these blocks are so large that even the memory buses cannot read them in 1 clock cycle. For example, if a block is an extremely large block, say for example 1 megabyte, probably no memory bus has a 1 megabyte width. So in that case, it will be broken up into certain number of collection of words, and then it will be reading. But still it is better than if they were reading in 1 word at a time. Then 1 megabyte reading will take a lot of clock cycles. Instead, if it is reading in 4 bytes at a time, it will take 1/4 the amount of clock cycles. Okay. And finally, the cache memory is very large. It can be very wide. However, the processor cannot work with so many words at a time. Okay. So remember, processor has one peculiar property. Processor does not, the cache and the memory can access more than 1 word at a time. Processors usually would not accept more than 1 word at a time. Okay. They would access only 1 word at a time from cache memory, and they will store it into their registers. Then maybe they will connect the next word and again store it in the register. That's why from a wide cache, you might have another address multiplexer which selects which of this cache memory word will be stored and finally will be brought to the processor. Now, what if you have multiple memory chips? Each of these are called memory banks. Okay. But your bus width is not that wide. Okay, it means it cannot cover all 4 banks, four chips at one go. Okay, what you do there is you access the electronics is such that you access this say memory bank 0, then you can access memory bank 1, then you can access memory bank 2, and then you can access memory bank 3. But the initial access latency from this point up to this point is only once. It happens only once. It's not that the initial latency is spent in accessing memory 0, bank 0, then again you spend the initial latency in accessing memory bank 1, again you spend for memory bank 2. That does not happen. So in general, this is the most desirable wide bus scenario is the most desirable construct. However, multiple chip DRAM computers have become very common. So you have slots on your motherboard where you can connect multiple DRAM chips depending on the motherboard. And because why? Because they want to give some flexibility. Say I have 8 GB of RAM. However, I am into gaming and all these things. I have a nice GPU in my laptop. I'm interested in gaming. I also require more memory that would help me. In that case, I decide, okay, let me put in another 8 GB RAM later on in my motherboard if needed. Okay, so slots are provided. So there might be slots for to slot in 4 RAM chips possible. So in that case, how do you calculate the latency? So suppose consider this wide bus, which is a forward wide memory. Okay, so this scenario. Miss penalty, this is in terms of number of clock cycles. Okay. Microprocessor clock cycles. The first one is one. Why was 1 clock cycle spent in missing? Because the processor searched in the cache and it could not find it in the cache. So 1 clock cycle is spent. Then this 15 is the access over bus. So over the bus, it takes 15 clock cycles. 15 is actually a quite small number actually. Okay, I mean, it's a quite small number. But anyways, I mean, the access over bus to and fro. Okay. Sorry. 15 clock cycles were spent. And finally, this one is another clock cycle was spent in transferring the data from this memory to the cache. Okay, no, sorry. After the transfer from cache to microprocessor, it reads in 1 clock cycle. So finally, what you have performed is you have spent 17 cycles. Okay, okay, these are bus cycles. Okay. These are bus cycles, but bus cycles and clock cycles might be different because I don't know what is what they are defining as bus cycles. Typically, bus cycles are slower than clocks. Means they are like they run at hundreds of megahertz. So 200 megahertz for a memory bus is probably a good speed, whereas your microprocessor might be running at 4 gigahertz. Whatever is the reason, whatever is the cycle unit, notice that you have been able to transfer 16 bytes. Why 16 bytes? Because you have 4 word you have been able to transfer. The bus can transfer 4 words at one go. And you took 17 cycles to transfer it. So overall bandwidth is, effective bandwidth is 0.94 bytes per cycle. Now in a 4-band interleaved memory, your bus width is ordinary. It is a 1 word. This is a 1 word wide ordinary bus. However, it can access multiple memories, and now the 4 words are distributed over the 4 memory banks. So how does the latency work? Well, you spend 1 clock cycle in missing, 15 clock cycles for the to and fro data transfer, to and fro this bus controller and other delays. And then now you take 1 clock cycle per word. Okay, so this is 1 clock cycle per word. So for 4 words, you spend you have been able to transfer 16 bytes, but now it takes 20 clock cycles. So it is your bandwidth is 0.8 byte per cycle, slightly smaller than the previous case. Now, more and more computers are replacing the magnetic hard disk drive technology with non-volatile semiconductor storage, flash memory. This is it has been for many years now being predicted. Actually, even from 1990s, early 1990s, people were predicting that magnetic disk will completely go out of usage and it will be replaced by an alternative technology. However, amazingly, magnetic disk technology has kept pace and they have improved the product quality such that they are still a very, very viable option. However, nowadays, for low amount of storage, flash memory is kind of the pervasive option everywhere in smartphones, tabs, compact laptops. Flash memories have become the mandatory kind of, because you cannot have a magnetic hard disk drive in a smartphone, then you would not be able to have a smartphone at all. They are built by NAND on, there are two types, NAND and NOR, non-volatile memory. They work in a very peculiar fashion by forcefully injecting charges through the gate of a MOSFET transistor. Now, from your electronics courses, rule 101 of MOSFET is gate current is 0. Okay, that is the rule 101. Okay, you start with that assumption. However, flash memory exactly works in a different way by forcefully pushing in current by creating large electric fields across the oxide layer, and stores values inside the devices in that way. They have extremely large integration density. Their speeds are smaller than SRAM, but almost approaching. And they have much lower energy storage than SRAM or DRAM even, sorry. But they are costlier. However, the cost is increasing. That's why most of the times they were being used in small memory cards. Okay. Nowadays they are being used in entire hard disk also. For example, I am teaching this class from a tab which has a flash memory. Otherwise, I use a laptop which has a flash memory. I believe many of you also use laptops or tabs which have flash memories, and all of us use smartphones which have flash memory. Okay, one unfortunate consequence of this forceful driving of current through the gate terminal, and just the way it works, the device works, is that the flash memories, every device have a finite lifespan. How many accesses you can do, how many read and write accesses you can do in the flash memory. Typically about 10 to the power 4 to 10 to the power 5 accesses per bit you can do. After that, it is permanently damaged. Means you cannot use it anymore for data storage. What to do in that case? In that case, if your entire disk has become unusable, you have to replace it. Alternatively, as it happens in our chips and flash memory chips and hard disks, they follow, first of all, two principles. The first principle, if it is saying that it has 1 GB of flash memory space, it probably has more than 1 GB. So that if some of the portions get destroyed over time, those are eliminated. So in the controller, there are inbuilt electronic controllers which detect which portions are usable, which portions are not usable. And they map your data to only those portions which are usable. So suppose you find, okay, out of 1 GB, 2 kilobytes in a certain location have become unusable. Fine, you can survive without this 2 kilobyte, and you will use some other portion. Okay, this is the first principle. Second principle is, this is a very interesting concept. They use something called wear leveling. They keep a track of which portions of memory have been accessed very often or how many times, and they try to map the read and writes to the entire, distribute the entire chips in a uniform manner over the entire chip, so that no portion of the chip is kind of accessed too many times. While some, like, it should not happen that some portion has been accessed 10 to the power 5 times and some other portion has not been accessed at all. That will not happen. You will find in a reasonable, these well leveling controller algorithms are implemented, and they are automatically, that happens. This address remappings of reads and write of these writes, that will distribute it over the entire chip, and you will find that more or less the entire chip has gone the same number of read and write operations. So they keep track of how much wearing has happened in particular portions of the chip. That's a very interesting concept. Okay. So the important thing to understand is that other than the raw module which holds the data memory, there are also some sophisticated electronics in these chips and hard disk drives. Now let us study a little bit of magnetic hard disk drives. Although they are slowly becoming obsolete. Maybe 10 years from now they will be fully obsolete, but you never know. You know, these people have been predicting that maybe 10 years from now it will be fully obsolete from the early 90s or mid 90s. This is 2021 and still they are a viable option. So they have been there for the last, I mean, people have been predicting that they will go out of use very soon. That people have been predicting for last 25 years. Still they are here. Okay. So that I am predicting within 10 years they will become obsolete. You never know actually. This magnetic disk technology is very surprising. Anyways, let us try to understand how it works a little bit carefully. This is a typical magnetic disk drive. The cover has been removed to show you certain characteristics. Usually disks are circular in shape. There might be multiple disks, maybe 3 disks. There are multiple these are read-write heads. These things are called read-write heads. Other than that, there is lot of peripheral circuitry involved, very, very complex circuitry. In fact, these are so complex that they contain chips inside which are themselves small scale processors. Hard disk drives, the reason why they are so expensive is they themselves contain chips inside which are processor like chips, which have their own assembly language in which they can be programmed and operate. However, the assembly language or the instruction sets of those processors typically are not exposed to the outside world. Only the companies which make these hard disk drives, they know about this. They are not general purpose processors, they are special processors which perform only this operation of. There are many things to control, as you will see very soon. All these controlling operations, their instruction sets are not made public. However, in the US, government research agencies have actually reversed engineered the processors. The processors typically work with small amount of code stored in small ROM memories inside this magnetic disk drives. They have reverse engineered the binary from that ROM and to figure out how the processor works, and they have used that in turn to infect the code of this ROM. So these attacks have been performed by researchers. Okay. Anyways, there is a central spindle through which this this entire assembly can rotate at extremely high speed. How fast it can rotate? Typical speeds nowadays is 7,200 RPM. Okay, 7,200 revolution per minute. Another speed is common speed is 5,400 RPM, but I think 7,200 nowadays is kind of more common. So they can rotate extremely fast. Now several technical terms have to be introduced. First of all, there is the data is stored in this circular portions called tracks on each of the disks. Both sides of the disks can contain data. So for each of the disks, both sides can contain data. If you have seen old gramophone records, they also usually used to contain songs on both the sides. So it is kind of similar, and read writes can be performed simultaneously or not simultaneously from both the sides. Okay. Data is arranged in the circular tracks. The smallest unit of data is organized in chunks in units called sectors. Okay, as shown here. Every track consists of several sectors. All the tracks at the same radius or across all the disks can be considered together in an hypothetical organization called a cylinder. The cylinder is not a physical cylinder, okay? It's just a hypothetical organization of the data across the different disks. What is the implication of a cylinder? Well, typically the read-write heads are they work at the same track across the different disks. So if it is reading the track shown here, okay, the second track, there actually it's more than two tracks, but if say this track, so if the read write head is reading from this track, it will read from the corresponding track on the next disk also and the corresponding track on the next disk also, which means across all the tracks over the entire cylinder, values are being read at the same time. Why is that necessary? That is necessary because the way the read-write head moves, the read-write head needs to move towards the center or away from the center. Okay. And it cannot perform any other type of movement. So either the read-write head moves towards the center. When it moves towards the center, it moves up to a track, but the same track across all the disks. Okay, so value can be read from or written to across the same track over entire disk. So value must be distributed. I mean, values or files must be written in a way such that if you want to perform parallel transfer of data from the same sectors, they must be written in a way that they are distributed across the different tracks, across the same tracks, corresponding tracks on different disks. Okay, so you cannot just say that, okay, I just on the same disk I will keep on writing the entire data. That is probably a suboptimal way of dealing with it. In that case, only one of the read-write head the read-write head would be reading only from one of the cylinders. Okay, one of the tracks, and the other two disks would remain. They will rotate, but they will remain idle because they do not have anything relevant to that file. That's not how it works. Values can be read simultaneously from the same track, and then they need to be arranged and combined. That combination should be done by the controllers present inside the hard disk drive. Also, once the read-write head reaches a particular position towards the center or away from the center, the disk must rotate to bring the starting point of reading or writing under the read-write head. The read-write head cannot rotate. It only performs to and fro linear motion. But this disk assembly can rotate. So suppose my read-write head has reached here. Okay, my read-write head is currently sitting here, but my starting point is here. In that case, the disk has to rotate this entire part so that this point reaches under this read-write head, and then it can start reading. Okay, so this concept that right track must be reached, this is called seeking. This is the movement to reach correct track. And then there is a rotation followed by a rotation. First seek happens and then a rotation happens. This is movement of disks to bring correct sector under read-write head. And the disk, not only the starting point, the next sector it has to read, the disk rotates again. The next sector has to be read, the disk rotates again. In this way, the entire track has been read. The read-write head must move either towards the center or away from the center. One important point to notice is the amount of data stored in the tracks is different for different tracks. Because the sizes of the sectors typically is constant, you can easily see that the tracks towards the center, because of their smaller circumference, has less number of sectors and they can hold less amount of data. Whereas the tracks on the outer side, they have more number of sectors in them and they hold more amount of data. Fine. So remember this diagram, and once we remember this, we can perform certain calculations to figure out what will be the throughput, okay, of this type of an electromechanical. See, this is an electromechanical system. Okay, there are motors, high-speed motors, etc. That's why it is quite difficult to decrease the voltage supply of a device which has a magnetic hard disk drive beyond a certain amount of point, because the motor and this mechanical part needs a minimum amount of voltage to rotate this thing at a speed of extremely high speed of 7,200 RPM. Okay, 7,200 RPM is a humongously fast speed. Okay, so that entire thing should come from that rotation is caused by the inbuilt motor, and that in turn needs minimum amount of voltage to be able to rotate it at that speed. So just cutting down on the supply voltage is not very easy. Another reason why cutting down on the supply voltage is not very easy, by supply voltage I mean the DC supply voltage, is the voltage at which the screens work. The screens are basically sensitive electronic devices, the touch screens and the modern LCD screens or LED screens. They require minimum amount of voltage to work. Okay. So typically you will find that although your microprocessor chip can work at the voltage of say 3 volt, 3.3 volt is very common, and the internal circuitry of the microprocessor probably works at a voltage of less than 1 volt, 1 volt or 0.75 volt or something. The motor, the screen of the laptop or tab, they require larger amount of voltage. That's why finally the DC adapters that you connect from your charging point, their output is typically in the order of probably 15 volts, between 10 and 20 volts probably. So you could have said, okay, why not push it down the output of the DC adapter to 3 volt? Then entire thing will be operating at a very low voltage. You cannot. Your microprocessor maybe and some other electronic chips might be able to operate at 3 volt. But other these electromechanical things or even the flash memory, probably it needs to create a field, a large electric field to cause read and write of data. Those, then the displays, they might not be able to work at such low voltage. So unless you get rid of this electromechanical system, this lower limit on the supply voltage that is possible, that will remain. Okay. Now let's see, suppose what does each sector store? Each sector stores the sector ID. It stores the data ranging from half kilobyte to 4 kilobytes. So this will be probably be more common. The trend is towards increasing sector sizes. Then it stores some error correcting code corresponding to the values in the sector. And there are the synchronization fields and gap between mandatory gaps between each sector, etc. Now, how do I access a sector? First of all, there is a queuing delay involved if other accesses are pending. What is this? For now, ignore this. I will explain it later. What is a queuing delay? What about other accesses? I will explain it later. If not in today's class, maybe some other class in the future. Fine. Then there is the seek delay. This is the read-write head delay. As I have mentioned, this is linear movement of the head. Then there is a rotational latency of disk, or maybe multiple disks. Then there is a data transfer needs some time. It can happen only at finite speed. And finally, there is this controller overhead. So these are the kind of the delay components involved. Unfortunately, this and this are depends on address. Why? Because very simple reason. Suppose currently your read write, as I said, suppose currently your read write head is here. Okay, suppose your read write head is here. It has to start reading from this point. So it first makes a linear movement inside. Then the disk rotates and it comes here. So how much linear movement it has to make inside? That is a degree of freedom. That depending on how much movement it has to make, the seek delay is variable. And then how much rotation has to be done, that also is variable. Because if by chance this starting sector had been just by its side, then it would not have been able to need to rotate that much. If the starting sector had been exactly here, then it would not have to rotate at all. Means rotate means it need to rotate when you read the data, but just initially there is no latency. So it is completely a matter of chance, and it's a kind of an unpredictable delay. That's why the delay you incur to read or write data on a hard disk drive is a function of the address on the hard disk drive. So that's why it is not constant, and that's why it cannot be classified as RAM. Okay, this is the reason why it cannot be classified as RAM memory. Now, so queuing delay that we'll discuss later may primarily seek, rotation, data transfer, and controller overhead. These 4 delays. So this is a typical example. Say I have 512 byte sector. It is rotating at 5200 RPM. This is too fast probably, but anyways. The 5 millisecond average seek delay. Okay, so typically these average seek times are mentioned. 100 megabyte per second transfer rate once the head comes at the proper position on the sector. 0.2 millisecond controller overhead, and the disk is idle initially. There is 0 queuing delay. Queuing delay has not been mentioned. How much time does it take to read one sector? That is the question. Okay. So average read time for one sector of size 512 bytes. Achha. 5 millisecond seek time. This is an average value. Okay. This is usually mentioned by the mentioned by the manufacturer. Okay, so we are using the average value. One thing to note is that the average sick time is usually extremely pessimistic. Experience has shown that the actual sick time is most of the times is better than average sick time. In fact, it can be as good as only 50% of the average sick time. Means average sick time is mentioned to be 4 megabyte, but actually it can be much less. Then the rotational latency is half divided by this. 15,000 divided by 60 is the time required for one rotation. Okay, and why is half being used, half being divided here as if half rotation is happening, students? Any answer? So rotational latency they are calculating by number of rotations divided by time for one rotation in units of millisecond. Okay. Now you tell me, why is half rotation being used? Hello? Hello, are you there?
Yes, sir.
Yeah, why suddenly half rotation is being used? What is half rotation? So what is the best case rotation? How much rotation has to happen if it is the best case? Come on, this is not a very difficult question, only common sense. So 0 rotation needs to happen if it is best case. One full rotation needs to happen if it is worst case. So they consider, because we don't know anything about the location of the sector, location of the read write head, etc. We assume half rotation happens. Okay, so these are typical calculations. Then is the data transfer rate. I have 512 bytes divided by 1000 megabyte per second, which is 0.005 millisecond. Controller delay overall 6.2 millisecond. Now, as I said, the average sick time is actually that is mentioned is usually so I should rather say that practical sick times are usually much smaller than average sick time. So it can be only 25% of the average sick time mentioned. In that case, if it is only 1 millisecond, the actual read time will become 3.2 millisecond. Okay, and then you can calculate the throughput. You have read 512 megabytes of data, 512 bytes of data in 3.2 milliseconds. So this is your kind of bandwidth. Okay, it is quite slow, very slow. Typically, if a lot of sectors are read one after the other, the initial rotational latency and the initial seek time is distributed over the several sectors, and then this bandwidth improves. Okay, so it is better if you have most of the data on one track and multiple tracks distributed across the different disks. Typically, these read-write heads have the ability to read in multiple tracks at the same time across different disks, and they also have the ability to read in from both the sides of the disks at the same time. So if there are 3 disks, each with 2 sides, and in the best case, your read-write head can perform 6 read operations from the 6 sides actually. Okay. So Yeah, so there are primarily two industry standards that I'll just mention in passing. One is called a small computer system interface, or SCSI. Okay, SCSI, and there is also an ISCSI, but it's called SCSI, but it is pronounced SCSI. And advanced technology attachment, or SATA. This is actually more common. Okay. This is what you have. These are just protocols and different protocols for how these things should work. This one is very common, and this is probably what you have in your laptops. These are two different protocols for two different types of systems. The SCSI, although it is called small computer, it is actually used in large warehouse scale computers which store humongous amounts of data. Actually, the iSCSI systems. Okay, and SATA is more common in the small computers that personal computers that we use. Now, disk drives themselves include flash cache to hold data. It can prefetch sectors in anticipation. They can anticipate that, okay, one sector has been read means next sector would also be read by the same process at some other time. What I mean by same process at some other time, I will come to it. Okay. That currently it is not being read, but maybe very soon the process would say, okay, I again want to read it, more data. So they prefetch sectors in anticipation of access in these caches to avoid the seek and rotational delay. So that the next time the process comes in and says, oh, give me the next amount of data, immediately it can transfer. For example, you are watching a movie, okay, that is there on your hard disk. The entire movie file, it's an HD movie, entire movie file is say 6 GB. You cannot load the entire movie file on your DRAM at one go because your operating system itself is taking up probably 1 GB of space. You have so many applications open, Google Chrome, you are talking with your friend on some maybe chat application. Okay, you are composing a document, playing games, doing this, doing that. After that, maybe only 3 GB of memory is left for you for your data memory movie file to be loaded. And the movie file itself is 6 GB. So of course it cannot be fully loaded. In that case, what happens is the operating system loads only certain portions of the file in terms of quantities called pages. So this is called paging, which probably we will also study a little bit. And later on, when you study operating system, you will study in great detail. Now, these pages are loaded into memory, say 3 gigabytes, and you start watching the movie. It proceeds normally. Okay. Now, your hard disk says that, okay, so this page for 4 pages have been sent. Maybe the 5th page will be very soon needed. So let me, if I am not doing anything else, let me fetch this page, next page of amount of data. Pages typically are like 4 megabyte or 8 megabyte in size. Those are larger than blocks. Say an 8 megabyte page, let me fetch it and keep it stored in a fast cache memory, semiconductor memory on the hard disk drive, so that the next time this movie, that process comes and looks for me, oh, I give me the next page because I need the viewer will see the next. I mean, the movie is progressing, so the next part of the movie has to be played. It can immediately transfer. Now, what happens is typically if you are watching the movie in a orderly fashion, by orderly fashion, I mean that it starts at minute and second, 0 minute, 0 second, and it will end in 2 hours, 0 minute, 0 second, set for a 2-hour movie. And if you are watching it uninterruptedly or at least in an orderly fashion, means you are not watching 0 minute, then suddenly you want to watch the 1 hour, then suddenly you want to see the ending and move to 1 hour 50 minute. If you want to access the file in an unorderly fashion, you will find there are delays involved, because your file system and operating system were not expecting, or the devices that is driver, whatever is memory to your memory, they were not expecting such unorderly access. Suddenly you push the cursor, push the slider to the end, you will find there is some delay before the scene gets loaded. However, if you are watching it in a continuous fashion, you will not find any stoppage or any delay, because just in time, in an expected manner, because your application is expecting what is the next page, it will ask the operating system will kind of arrange so that this page will be ready for you when you want to view it, when you want to view its content. Okay, so any orderly expected access of data can be satisfied by the operating system and accompanying hardware and the application. But unorderly access of data, typically for large files, they create problems, because you are breaking the principle of locality. Principle of locality expects that only the portions of the file which are nearby to the current portion of the where your file pointer is, where currently you are reading from or writing to, only those portions you are going to access. However, the moment you violate the principle of locality through your usage, the system will adapt, but the system will need some time to adapt. And there will be a impact on the viewer experience. You will find that there is some latency. Okay, and these things will be more clear when we study the next topic. Okay, so I'll take a 5-minute break, because now I'm going to shift to another set of slides. And when we come back, we will continue with this discussion. So I will now divert slightly and I will teach two topics in very brief from the operating system textbook by Galvin. This will also be your textbook next semester, the operating systems course probably, the standard textbook worldwide. So I will cover very small portions of chapter 3 and later maybe chapter 13 or so. I won't need to cover everything. I will just cover it to give you a flavor of, or to introduce you to certain concepts called interrupts, vectored interrupts, how the IO system works in conjunction with the microprocessor, etc., etc. These are important, although these are not that difficult concepts, especially you will study it now, later on again you will be probably be taught this in your operating system course. Although these are not difficult topics, surprisingly year after year we find that in the grand vivas or during student vivas, during project presentations, basic concepts related to this, when these are asked, many students cannot answer correctly. Why that is the case year after year, we don't know, because we more or less teach the exactly the same topic using exactly the same textbook. Because these are very standard topics. Okay, I mean, it's not that it changes every year. It's not like that. But somehow students, they have a lot of confusion and they cannot answer it. Anyway, so try to try to pay attention. Now, an operating system is a software that resides on your computer and it manages the entire execution of the computer. It ensures that all the processes who are trying a program in execution is called a process. Okay. So process is a program in execution. Process execution usually progresses in sequential fashion. Okay. Instructions for executable files typically are first from hard disk, they are loaded into memory. From there, they are loaded into cache portions of it. And finally, they are loaded into the microprocessor one after the other and executed. Typically, we have two different cache memories. This is also something new that you are going to learn. Till now, whatever cache memory I have mentioned, I have not mentioned whether the cache is shared between data and instructions. The memory, the DRAM chip is shared between data and instruction. No problem. But in modern computers, there are two separate caches. One cache exclusively handles the instructions and the other cache exclusively handles the data. One is called an instruction cache or I cache, and the other is called a data cache or D cache. Okay. In your MIPS 32 programming and in the SPIM simulator, you have not at all obtained any flavor of any cache. You are just, there are some addresses, abstract addresses, and you are performing loads and stores to those addresses, from those addresses or to those addresses. However, those abstract addresses are all, later on you will find they are all kind of, it is not transparent to the application programmer. We do not know what is the actual physical address. The virtual address to physical address translation happens in the background and is performed automatically by the hardware in conjunction by the operating system in conjunction with several hardware. Anyways, we will see that later. Operating system usually executes a batch variety of programs in a batch system where one job finishes and the other job starts. So this is kind of the old technique. Okay, say 1960s. And the second, or say 1950s, I should say, 1960s, time sharing had started getting popular. And time shared system, this is the uh, uh, important concept where there are several users usually, okay, multiple users, and each of these users can be executing multiple tasks at the same time. Okay, however, not all these tasks can be executed by the microprocessor simultaneously. This is a very important concept which again surprisingly students do not fully understand even at the end of a BTech degree, sometimes even at the end of a MTech degree we have seen. A microprocessor cannot execute two programs at the same time. Okay, it can execute multiple threads of a program at the same time, but that's a different issue. Okay, we'll not go into it in this course. Maybe if you take the HPCA course, the dual degree students will study the HPCA course, and also in your operating system course, you will learn about threads. In general, the microprocessor is executing only one program at any point of time. However, it continuously keeps on changing between this program, then another program, then another program, in another program in a round robin fashion. Typically round robin fashion, there might be other schemes also, but round robin is very popular. Okay, so process number 1 gets some time chunk on the microprocessor, followed by process number 2, followed by process number 3, etc., etc. Because no modern computer runs only one user process at a given point of time. Multiple processes are running, and multiple processes have to be handled at the same time. There have been relatively new operating systems which could execute only one user process at one point of time. Example was MS-DOS. MS-DOS was quite popular till the mid-90s before Windows 95 became popular. Okay. Till now, MS-DOS emulators are available. The command prompt is available in all Windows, whatever version of Windows you are using. MS-DOS, you could run only one user program at one point of time. So there was no concept of a browser running. You have kept it minimized. You are typing something on a Word document. Then again, you minimize the Word document and you look at the browser to see whether any email has come. Again, you go back to the Word document, nothing like that. You either work on one application, you finish that application, save the files, etc., come out of it, invoke another application, work on it, completely exit the application, then again go to another application, etc. So it was quite inconvenient. However, people could work on it because it was it was considered easy to use. It could run on relatively low-end computers called like PCs, whereas full-fledged Unix before Linux came out was quite difficult to learn, or was quite difficult to run on single computers. Okay, it was tough. The versions that were available on Unix, uh, uh, which were suitable for single person usage, were extremely expensive. Okay, so people could not afford so much of money, and it required very high-end computers to run. Because Unix from the very beginning was time shared, and from the very beginning it was multi-user. MS-DOS was a single user operating system. Okay, only one user could log in at any point of time and work. Microsoft operating systems were all single user, Till I believe Windows NT came out towards around 2000 or so. NT is for new technology actually, I believe. So till Windows NT came out, it was exclusively single user operating system, and MS-DOS was single user, single process. Okay. And Unix on the other hand was developed in the late 1960s, early 1970s. From the very beginning, it was multi-user, multi-process. So extremely high-end in a sense. Okay. And that is the common paradigm that is followed nowadays. Linux was developed to be present a similar interface as Unix, because Unix was not free software. Large parts of the code were licensed by AT&T Bell Labs. Although some universities tried to port it, but still some portions remained copyrighted with AT&T Bell Labs. So this Linux was developed by Linus Torvalds, Finnish master student. That was his master's thesis project, basically, the Linux kernel. It presented an interface similar to Unix, but it was written from scratch by that one single person, and later on many people contributed and it became popular. It exceeded its initial scope of being a substitute for Unix on single small computers. It started running on servers, and most of the largest servers and supercomputers nowadays use some version of Linux. Anyways, processes typically include a program counter, a stack, and a data segment section. So this we have seen. I'll go through very quickly. This all of you have seen the general memory image of a process. These are all virtual memory images. Okay, I mean it gives as if it gives a continuous. The entire memory is available for each process between the range 0 to some max. But of course, that is not possible. So these addresses, virtual addresses, are getting mapped to some physical addresses. Luckily, no process uses its entire address space at one go. And even if it wants to use, it is not allowed to use, okay, by the operating system. Only certain portions are allowed to be used. Certain portions are brought into memory and executed. Certain portions are brought into cache and executed, etc., etc. Now, this is a very important concept. A process in a computer has several states, and it keeps on changing state continuously. Okay. When it starts, it is in a state called new. When then it is running, when instruction waiting state, a ready state, a terminated state, etc., etc. We will see the process state diagram. So next semester when you study operating system, again this will be taught. But here we need to understand this because we need to understand interrupts. Okay, that's why we are being forced to study this. I'll explain what is an interrupt. Initially, the process, when it is invoked, suppose you double click on an icon, a process is invoked, corresponding process is invoked. It is in a new state and it is admitted. Okay, it is said that it is admitted by the operating system and it waits in a ready state. So this is the state transition diagram of a typical process. This ready state is the process. In the ready state, the process waits in a queue data structure maintained by the operating system kernel called a ready queue. Why do we see a data? Why is a process a data structure? Because the process descriptor is stored in a data structure called process control block, or PCB. That also I think we will see very soon what is the basic structure of it. It is literally a C structure, okay, in the Linux kernel. It is a C structure, struct type thing. And it is stored in different fashions. It can be stored as a linked list. It can be stored as, typically it is stored as a linked list queue. Implement queues, you know, can be implemented in several fashions. Now, when it is in the ready state, it has not yet been assigned the microprocessor to run because some other process is running. However, because of certain events called interrupts, the microprocessor is told that some other process was in the running state on the microprocessor. This running is okay, it is happening inside microprocessor. In the admitted state, it has been brought into memory and it is waiting in the ready queue. Okay, so ready queue typically can be a linked list like this. So this is kind of your head of the queue. This is the one that can be sent into the running state later on. So this is the one that will be selected next. Now, some other process is running. Okay, it is happening inside the microprocessor. Because of certain conditions, that process is interrupted. How it is interrupted, we will come to it. That is a very interesting mechanism. Somehow the microprocessor is informed that, look, currently you are executing process A, you have to stop its execution. The process is not informed that you have to stop execution. Okay, this is another major misunderstanding of students. Why, I don't know. They answered somebody, the operating system tells the process that you have to stop execution. Right? Where is the operating system coming from? Operating system itself is a software. The operating system is currently not running. It is not a magic software that it can run on its own without a microprocessor. Currently, the microprocessor is executing some process A. Nowhere the operating system is there. Means it is there. Finally, the operating system will come for execution, but not immediately. The process somehow is informed by somebody through an electrical signal mechanism, which we will study. Okay, that you have to stop. I mean, the microprocessor is informed, sorry, that you have to stop the process that you are executing currently. Please stop it and please do something such that the next process, I mean, don't think about what to do next. Look at the interrupt signal that has come. The interrupt signal typically gives some hints to the microprocessor of what to do next, which program to start executing next. Just do that. The next program that will be executed will handle the others. So this process is sent out. Okay, sent out means the state is saved, and then the processor starts executing another program which decides that, okay, I can push the next process that is waiting in the ready queue for execution. This module is typically called the scheduler of the operating system. Okay, this is an operating system module which arranges through a mechanism this thing that the next another process, say B, will start executing. So from A it went to scheduler. Actually it does not directly go to scheduler, but anyways, as a simplicity, you assume it goes to scheduler. Then from that it goes to another, say, process B. Okay, so this process B was selected by scheduler. From the ready queue. This process of another process B going from the ready state to the microprocessor, this is called a scheduler dispatch. That is the technical name. Scheduler does not physically take the process and dispatch it to the microprocessor. It just makes the microprocessor program counter point to the starting address of the next process B. Not the starting address, just the instruction from which next process B should continue. So in the meantime, process A is sent back. So B was initially, process A is now sent back towards the back of the ready queue. Okay. So this now becomes process A. The back tail of the queue is modified, and process A now goes to the back of the ready queue. Why to the back of the ready queue? Because process A is so, you just now you had a hold of the microprocessor. We have to share it between so many processes. You just now had your hold. You go and wait the end of the. When your time comes, again you will get hold. In the meantime, B starts running, and so B starts running. Okay. When B starts, after B starts running, it can either now it can also happen that it can exit normally. So it goes to the terminated state and it just goes out of the system. Basically, all its memory resources are freed, and the operating system completely destroys the memory image of the process, releases all memory held by it, releases the process control block that it was holding, etc., etc. However, a more common event is an IO or event wait. This is primarily important in the context of HDD operation. Both the interrupt is also primarily important. So both these you should understand how it works. What is an IO or event wait? Suppose you have a scanf function in your C program. This is an input output event. Nobody can predict when this event would finish, because the speed at which the person would enter the value corresponding to the scanf function call is unpredictable. The operating system does not allow the processes to keep occupying the microprocessor, because the microprocessor is a precious resource that is being shared among several processes. All of these processes are in memory. Okay, all of them are in ready state. Everybody wants the microprocessor, but it can only handle one process at a time. What the operating system does is it does a common sense thing. It says, look, first of all, if an IO event has to happen, it is so slow. Okay, extremely slow. There is no point making this process wait in the microprocessor. I will push it to the waiting state. I will make it exit the microprocessor, push it to the waiting state, and I will consider the next. This had been removed from the wait queue. Next process, maybe it was C that was in the waiting ready state. I will push it to the microprocessor so that it can start executing. Now, what happens in the waiting state? Well, in the waiting state, there are further queues called waiting queues. So these processes that were evicted from the microprocessor, they are waiting in waiting queues. Okay, the waiting queues there can be several waiting queues, as we will see next. Several waiting queues are for several slow devices, like an keyboard through which a person enters something, a hard disk drive in which read and write operations takes millions of clock cycles, etc., etc. Human being typing something on keyboard is the worst. I mean, it is probably the slowest thing that the computer experiences. Okay, we type, human beings react at extremely slow speed. So there also it keeps waiting. When will my user type in something, etc. Then there can be waiting queues for the IO devices like hard disk drive. As I said, hard disk drive is an IO device. There can be a waiting queue for printer process that is printing a page on a printer. This is also very, very slow process, etc., etc. Why there can be multiple processes in a waiting queue for the hard disk drive? because multiple processes might be trying to access the hard disk drive at one go. So how does it look like? So for example, a ready queue and various IO device queues are shown here. So this, suppose there is a disk. Okay. The disk has several process control block data structures as linked list nodes. Currently, 3 processes are waiting. The PCB process number 3, process number 14, and process number 6 are waiting to access the hard disk drive. But hard disk drive, as you know, will be able to access only one process will be able to handle only one process at one point of time. So currently, suppose it is handling process number 20. So once it gets done with process number 20, it will start processing process number 3. Additional pointers might be maintained to directly point to the head and the tail of the linked list. That's a data structure specific, how the kernel operating system has implemented this data structure, those type of details. In the ready queue, it is also a linked list implemented queue, except that in the process control block data structures, you also have to store the snapshot of the state of the process. Okay, typically means the register contents. When the process was evicted. Because the process will start from that point. It will not start from the beginning, right? Evicted from the microprocessor. This is the state. And there are several other things also, process IDs and all this, many other list of open files, what are the other resources the process is holding, all things. If you want details of the PCB, you can PCB data. This is a just a C struct. Okay. If you want the detail of this, you can either search for Linux process control block structure, or you can also have a look at the Galvin textbook. I think the Galvin textbook also gives a description of the C structure corresponding to the PCB. Fine. And this is the terminal unit, that is screen. Currently, many processes probably are waiting to display stuff on the screen, but only one process can display. So the other processes keep waiting. Magnetic tape is very old fashioned. This is very old. This has gone out of. This was similar to cassette type technologies. Okay, those of you who have seen these old audio cassettes, those type of things. And these were earlier days, those were useful, but nowadays they are not used that much. Okay, so this is the situation, typical situation of these wait queues. So one important thing to understand is when a system is in the wait queue, its priority is very, very low. The waiting state means process is not under consideration to run. This is also another major misconception we find among students. They say that processes in the wait state are waiting to occupy the microprocessor. No. The processes in the wait state are waiting for some other event to complete, not for the directly for the microprocessor. They will eventually also need the microprocessor probably. But initially they are waiting for some slow IO devices like hard disk drives or some other IO devices to complete their operation. Only then once that event completes, there is an event completion signal sent. When that happens, the operating system, it can make special status registers to show that that is done. And then the operating system checks those status registers and sees, okay, so this device is done with its business. Then it sends the process again to the ready queue. How does it send the process to the ready queue? By again sending it to at the back of the ready state by sending the process PCB at the back of the ready queue. Okay, so this thing keeps on continuously happening. After some time, again, that process would probably come to a running state. If no IO event happens, there can be processes which have no IO events, which just performs pure computations, doesn't store any files, doesn't read in data from files, doesn't perform any printf or scanf operations. Yes, can happen, but then that process cannot keep occupying the CPU indefinitely. After some time, typically at intervals of about say 10 to 100 milliseconds, they will be mandatorily evicted from the microprocessor by this interrupt mechanism. There is something called a timer interrupt that comes. As soon as process starts running, the operating system starts a down counter by seeding the down counter with an initial count value, okay, corresponding to what is the microprocessor clock frequency, and what is how much time it wants to give to the process. Suppose it wants to give 10 milliseconds to the process, and the microprocessor clock frequency is, suppose it wants to give 1 millisecond to make calculations easy. So it will give a time interval delta of 1 millisecond for the process to run, and your microprocessor clock frequency is say 1 gigahertz. So in that case, it initializes the, so basically 10 to the power, this is like 10 to the power 6 clock cycles. It initializes the down counter with 10 to the power 6, and the down counter starts counting down. When it reaches 0, it sends an electrical signal to special pins of the microprocessor telling that the time quantum that was allocated for the process that is running now is over. The operating system cannot inform this to the process or the microprocessor because the operating system is not running. The scheduler, once the scheduler dispatch happens, the operating system is evicted from the microprocessor. Try to understand this. The operating system is just another software running on the microprocessor. It's not a magic software that it will not require a microprocessor to run. What happens is, because of extremely fast change between processes, change from process to operating system modules, back to processes, again to another process, this thing keeps happening so fast at intervals of 10 milliseconds or so. The human users do not understand any, what should I say, any disruption in work. They think that the process that is he is working with currently is the only process running on his system, and that process is entirely occupying the microprocessor. For example, right now I have some sort of a document viewer app open through which I am displaying the the slide, but you are getting the screen sharing through MS Teams, which is a completely different software. To me, as if I am working only with the document viewer and the PDF I am writing on the PDF, etc. It's not the case. Of course, the MS Teams software is also running. How is it running? Because it is being given the opportunity to run at repeated frequent intervals of time. This kind of a system where every process is given certain time quantum to run, then it is evicted. The partially executed process is evicted. Again, after some time, it comes back. Again, it is evicted, and this cycle keeps on happening. It's called round robin scheduling, and this is the most common type of scheduling. Scheduling is a huge topic. In operating system, you will learn that what are theoretically optimal scheduling strategies, how does an operating system perform scheduling in practice, etc. These are not very simple topics. Okay, they are quite complicated topics. Okay, round robin scheduling, I just said that, okay, give every process 1 millisecond or 10 millisecond or whatever, and then decide. However, how much time to give to each process? Should we give the same amount of time to each process or unequal amounts of time to each process? All these are important things that the operating system must decide. Okay. So in the waiting state, a process is not even under consideration for getting executed. When the event is done, again the hardware through some signaling mechanism to the operating system says that now it doesn't disturb the microprocessor. It just disturbs the operating system kernel. It makes certain registers at some certain values and waits when will the kernel module come and check those registers. When the kernel module comes and check those registers, it can see that well work is done and it pushes the event to the ready state. An alternative is that it can send another interrupt to the through another piece of hardware. It can send an interrupt to the operating system through a process called DMA or direct memory access. We will study it very soon, but that is slightly more advanced. But anyways, this is how it continues. So how does, in terms of time, how does it look like? The continuously this thing keeps on happening. The times for a process P0, say, okay. So this is the first. This is the first one occupying the microprocessor. Then it is the second one operating system module, and then this will be the third one. Okay. How does it? How does they work? Or how do they work? Process P0 is initially executing. At this time, suddenly there is an interrupt or system call, and the operating system starts executing. The operating system can also be invoked through system calls. Okay. For example, if you try to execute a printf function, at the background there is a system call. Okay, that is not clear, but it is actually a system call happening, and the operating system has to. Similarly, if you want to perform a fopen function call in C, at the background another system call is happening. Okay. So the operating system module gets invoked. It has to save the state of process P0 into PCB0. Okay, then it does some more work. It's work that was needed, and then it decides that well, the process 1 should start now. So process 1 suddenly starts executing. Till that point, process 1 was idle in. Process 1 was sitting idle in ready state, not doing anything. Okay. Now, so from this point onward, process 1 starts running. It runs for some time, but again at this point there is an interrupt or system call. Again, the operating system takes back control by, it is helped into taking back control by the interrupt mechanism of the microprocessor. It saves the state of the PCB1 on the ready queue maybe, and does some more work, and it reloads that PCB0. So there are only two processes in the ready queue. Okay, two process. This is the two process, two user process plus OS system. But two processes typically are very low number of processes. Typically, your system will have tens of processes. Okay, but anyway, here to make things simple, again it loads PCB0, and again the control goes to PCB0. The microprocessor is loaded from the saved state, and again it starts executing. In this way, in a ping pong fashion, control goes on between PCB process 0 and process 1, P0 and P1 again and again and again, with the operating system playing an intermediary role. This process of okay, process change in process being executed on the microprocessor. This is called a context switch. A context switch is an overhead. Okay, it does not perform as such any useful work. What is the context switch time here? If you see in this interval, only the OS module was running. Neither process P0 was running nor process P1 was running. If we assume that the user is only interested in process P0 and process P1, this idle time where both process P0 and process P1 are idle, this is the context switch overhead time. The context switch overhead time, this should be as small as possible. And they are as small as possible. Typically, this context switch overhead times are, if you are giving a time quantum of delta for each process, typically they would probably be in the order of 1/10 of delta or something. Okay, so the diagram is not correct. The diagram makes it look that as if the context switch itself takes almost same amount of time that a time quantum is given to a one process. It is not correct. The context switch time is very fast, and the operating system have been very optimally implemented so that the context switch time is minimal. Okay. Okay, so let us stop here. It's beyond 12. I didn't notice it. Sorry. We will continue from this on Thursday.